Hi students, in this class we will see the SLG fault or single line to ground fault of an alternator. We can classify the power system faults into symmetrical fault and asymmetrical faults. In the symmetrical fault, we study the three-phase to ground fault. In the asymmetrical fault, we have SLG fault or single line to ground fault, then line to line fault, then double line to ground fault. In this class, we will see the analysis of SLG fault or single line to ground fault. In the fault analysis, we will see the fault current using the three sequence networks, using positive sequence, negative sequence and zero sequence network. We will find out the fault current when an SLG fault occurs. Let me draw the equivalent circuit of an alternator. It consists of a voltage source in series with the reactance. This is our A phase. This is the B phase. This is the C phase. The three phase voltages are EA, EB and EC. The phase impedances ZA, ZB and ZC. The three phase impedances are equal, so we can mark this as Z. And we have a neutral grounding impedance. This is Zn. The three phase currents are IA, IB and IC. This is an unloaded alternator. So the currents in the three phases will be equal to 0. This is a balanced system. When you find out the sequence networks for a balanced system, we will get only the positive sequence network. Why this is a balanced system? Because the three currents are 0 and they are equal, and the voltages are also equal in magnitude and are separated by the equal 120 degrees. So this system is a balanced one. So you will get only positive sequence network for this particular system. Now suppose a fault occurs in the first phase. So this current is no more equal to 0. So this is for IA. This is the fault current. So this is shorter to ground. That's why we call this a single line to ground fault. Only one of the three lines is shorter to ground. In the other two phases, the current is still equal to 0. Now, the system is no more balanced because the three currents are not equal now. Once the system becomes unbalanced, the negative sequence and the zero sequence components or these two sequence networks will also be added with the positive sequence network at the point where the fault occurs. Once the system becomes unbalanced, you will get positive sequence network, negative sequence network and the zero sequence network at the point where the system is unbalanced. Now the thing is, you need to find out the interconnection of the three networks. How these three networks, positive, negative and the zero sequence networks are interconnected. Whether they are connected in series or in parallel or in series parallel combination. For that we need to find out the sequence currents and the sequence voltages. From that value, we can understand the interconnection of the three networks. Here IA equals IF and IB equals IC is equal to 0. As this point is shorter to ground, the A phase voltage will be equal to 0. Because this is shorter to ground, so the voltage becomes 0. Now let us find out the sequence currents. IA0, IA1, IA2. So this is equal to 1 by 3 into the transformation matrix is 1, 1, 1, 1 alpha square, 1 alpha, alpha square, 1 alpha square, alpha. Here the phase currents are IA, IB and IC. Here IA equals the fault current IF and IB equals 0, IC is also equal to 0. So from this expression, IA0 equals 1 by 3 into 1 into IA plus 1 into 0 plus 1 into 0. So this is equal to 1 by 3 IA. Similarly, IA1 equals 1 by 3 IA. IA2 is also equal to 1 by 3 IA. Let me write the sequence currents here. IA0 equals, IA1 equals, IA2 equals 1 by 3 IA. So here the three sequence currents are equal. So the three sequence networks should be connected in series. Positive sequence, negative sequence and the zero sequence currents are equal. So the networks are in parallel. Now look at the voltage equation. The phase voltage is 0. As you know, the phase voltage equals the sum of sequence voltages. VA0 plus VA1 plus VA2. This is equal to 0. The sum of the three phase voltages equals 0. So there should be a short circuit across the series combination of the three networks. Let us draw the three sequence networks now. Let me draw the positive sequence network first. In the positive sequence network, we have the positive sequence impedance and a voltage source. Here the current is IA1, the positive sequence current. The voltage is VA1 equals the source voltage minus the drop IA1 into Z1. This is the positive sequence network. Now in the negative sequence network, there is no voltage source. We have only negative sequence impedance, Z2. Here the current is IA2. Negative sequence voltage VA2 equals, there is no voltage source. So it is 0 minus IA2 Z2. Or it is minus IA2 Z2. Now let us draw the zero sequence network. This is the zero sequence impedance of the alternator. Now when you draw the zero sequence network, you need to consider the neutral grounding impedance, because the zero sequence current flows through the neutral grounding impedance. But when the neutral grounding impedance is marked in the zero sequence network, this should be marked as 3ZL. So the current is IA0. We'll see the reason for that. The three zero sequence currents will have the equal magnitude. This is IA0, IB0 and IC0. IB0, this is IC0. All are equal in magnitude and in the same direction. So in all the three phases we get the same zero sequence current. And these three zero sequence currents will be flowing through the neutral grounding impedance. So what is the total current flowing through this Zn? It is 3 IA0. It is IA0 plus IB0 plus IC0. So the A phase zero sequence currents will flow through 1/3 cross section of this impedance. And the B phase zero sequence currents will flow through 1/3 cross section of this impedance. And through the remaining 1/3 cross section, the C phase zero sequence currents will flow. So we can split this into three portions. When the cross section is 1/3, as you know, the impedance will be 3 times. 3Zn, 3Zn. This is also 3Zn. If you find out the parallel combination, the value will be Zn. So through this portion, IA0 will flow. And through this one, IB0 will flow. And through this reactance, IC0 will flow. So when you draw the zero sequence network for one phase, you need to consider the impedance for that particular phase. So we are writing the voltage at this point with respect to ground. This is Z0. When you draw the zero sequence network, this is already marked here. The current is IA0. So now, what is the impedance in this portion for the A phase? IA0 into 3Zn. That's why 3Zn is marked here. So VA0 equals minus IA0 into Z0 plus 3Zn. So the neutral grounding impedance Zn should be marked as 3Zn in the zero sequence network. The actual neutral grounding impedance is Zn. But when you mark it in the zero sequence diagram, so this should be treated as 3Zn. Now look at the sequence current equation. The three sequence currents are equal. So these three networks should be connected in series. So here IA0 equals, IA2 equals, IA1. Now look at the voltage equation, sequence voltage equation. VA0 plus VA1 plus VA2 equals 0. The sum of the three voltages equals 0. So there should be a short circuit across this series combination. So the sum of VA0, VA2 and VA1 will be equal to 0. Here the current is IA1 equals IA2 equals IA0. That's the current flowing through this part. We need to find out the fault current. The purpose of the fault analysis is mainly to find out the fault current. What is the fault current here? IF. IF equals IA. We have to write everything in sequence components. And IA equals 3 times IA0. IF equals IA. This is equal to 3 times the sequence current. The three sequence currents are equal. So this is equal to 3 into, what is the sequence currents flowing now? What is the current flowing through this sequence network now? It is the total voltage divided by the total impedance. The voltage is EA. What is the total impedance? Here it is Z1 plus Z2 plus Z0 plus 3Zn. Z1 plus Z2 plus Z0 plus 3Zn. So this is our fault currents now. Now we have considered a dead short in the first phase. Now let us add one more step here. To consider a fault impedance ZF. So the fault occurs through a small impedance. This is our fault current. Now what is the voltage at this particular point with respect to ground? It is IF into ZF. So the voltage is no more equal to 0. This is IF ZF. So the sum of the sequence voltages become IF. So this is equal to IF ZF. What is IF? IF is equal to IA. IA equals 3 times IA0. So it is 3 times IA0 into ZF. We have to write everything in sequence components because we are using the sequence networks to find out the fault current. It is 3 IA0 ZF. The sum of the voltages equals, this is no more equal to 0. This is, the current is IA0 here. So this is 3 ZF. The fault impedances should be marked as 3 ZF in the sequence network. So now let's find out what is the fault current. This is 3 times IA0, which is equal to 3 into total voltage by total impedance. Now one more element is added in the impedance. This is 3 ZF. Now this is the fault current. If it is a dead short, the fault impedance will be 0. You will get the remaining terms. Now if you look at this expression, we can find out when you have this ZN, neutral grounding impedance, it helps us to reduce the fault current because ZN is in the denominator. So when you connect a neutral grounding impedance, this will help us to reduce the fault current when a single line to ground fault occurs. Now if you increase this value, what will happen? Obviously the fault currents will reduce. Suppose you are increasing this up to infinity. What is meant by infinity impedance? This is an open circuit. If this is opened, what will happen? This Zn is equal to infinity. So what is the fault currents now? IF will be equal to 0. Now you may wonder why we should connect this neutral grounding impedance. Instead, if it is kept opened, the fault current becomes 0. That is what we need. But there is a disadvantage with the neutral grounding kept opened. We will see it. Now suppose a dead short occurs at this particular point. What is the voltage at the other two phases? Now this terminal voltage VB and VC will be increased. What is the voltage at this point? This is equal to this voltage plus this voltage with respect to the ground. This is our ground now. When the fault occurs in the A phase, this is our reference phase. This is our reference. So VB equals the voltage across this winding plus the voltage across this winding. You need to find out the vector sum of these two voltages. So what is VB? VB will be equal to the vector sum of these two voltages. So this is V phase plus V phase, or V phase A plus V phase B. Actually this will become root 3 times V phase. When this is grounded, when the neutral is grounded, this voltage will be V phase. But if the neutral is kept opened, if it is ungrounded, when a single line to ground fault occurs in one phase, in the other two phases, the voltage will be increased to root 3 times phase voltage. So the insulation requirement in the other two phases will be greatly increased. That is the major disadvantage of the neutral being opened. So that's why the neutral must be connected to ground through an impedance. If you connect an impedance, the fault currents can be reduced. So this is the fault currents considering the neutral grounding impedance and a fault impedance.